Hello. So we're going to talk about um, terminology review for dynamics. So this dynamics here means in Chinese is 动力学. It's Newton's law and also the uniform circular motion. Okay. So first things first, let's talk about force, right? So force is a vector. So it has both direction and magnitude. And force, there are many different kinds of force, right? So we talk about a translational force. Well, this term is not really used a lot, but when we say force, a lot of time we talk about translational force, means that we pull it and then it accelerates. Okay, and that's the only force. There's no friction. Then we know, right? This force it relates to the acceleration that way. Okay, so that's doing translation. So this motion here is the translation, right? So translation can also be if you are in the space and you're only one force going that way, then it will be translating this way. Okay, so that's still translation. Number three, it's called centripetal force. So we don't have a special name for it, right? Just F. Centripetal force, we do have a special name. So we call that FC, right? Well, this translational force, is related to net force. We'll talk about that. So centripetal force is actually, it's a special net force, right? So what does that mean? I'm going to change color here. It means that if I have an object like a satellite and it's moving, right, around the Earth, satellite. In Chinese, this is called 卫星,人造卫星. Right? Okay, so it's going around like that. And how come it's not being attracted, and how come it doesn't like go toward the Earth? Because it has a velocity. If the velocity is equal to 0, then it will go, right? It will go toward the Earth, right? So then the net force that's pointing to the center, so that's why it's centripetal, pointing to the center, this one here, it's called the FC. So it's a net force, but it's a special net force that's going toward the center. So it's the net force that going toward the center. Okay, all right, I'm going to clear that and I want to continue. So number 4, we're going to talk about net force. So what is net force? So usually the net force we're talking about is more referring to a translation. 移动, okay? So in Chinese, this is called 移动. Okay? So if you have a force going this way, and then the friction that's going this way, let's say, right? Then, well, you also have the mg and n. Let's just get, they cancel, right? In this case. So the net force from all these 4 forces, this net force, Fn, is equal to this 4 add together, which is equal to F minus F. That's your net force. So this is your net force. So it's just a sum of all forces. All forces. Okay, acting on this system, this object here. So that's so-called the net force. So FC, centripetal force, is similar to this net force, but it's pointing toward the center, okay? And not just that, FC is perpendicular to the velocity of that object, okay? In this case, the net force Fn, is equal to the m times, this is m, times the a. So A and Fn always same direction. Same direction, because m is just a scalar. Okay? So if something is accelerating, there must be a net force. If there's a net force, then it must have some kind of acceleration, and they will be at the same direction. Same thing as FC and the AC. They must be the same direction. If there's a net force pointing to the center, then there must be a net acceleration that's pointing to the center. Okay? All right, so let's continue. All right, so that's the net force. Clear that. Okay. So what else? So let's talk about tension. Right? So tension is a force, right? Special force that's in the string, right? In a string, right? In a string, or a thread, or a rope, or a cable, right? Okay, so that's tension. Okay, and so if you have a string, usually we assume string has no mass, so massless. And if you pull this way, and it's not, let's say it's in balance right now, so there must be another tension that going this way. Okay, so that's tension. And normal force, so it's N. So it's not Newton, but it's a symbol for the normal force, right? So this is a contact force. So you must have contact to have normal force. And this is also a supporting force. So for example, the chair is supporting you, right? This chair, and you're sitting on the chair, right? So this chair must be supporting you. So that's a supporting force. Also, the normal force is an electrostatic force, but we're not going to talk about that. It's a one kind of magnetic force. All right, so it's one kind of electromagnetic force. So that's normal force. And then we have gravitational force. Okay, so gravitational force is Fg, which is equal to a mass times its gravitational acceleration, right? So this is just a subscript. So that's also is defined by the universal gravitational law. So m times me divided by r squared. Okay, so this is called UGL, so universal gravitational law. Okay, so UGL, right? So this here is a constant. It's called universal gravitational constant. Universal gravitational, or constant of universal gravitational constant. Okay, and that's equal to 6.67 times 10 to the negative 11, and the unit is Newton times meter squared divided by kg squared. And how can you tell? Because this is in Newton, and this one here is a meter squared, and this two together is kg squared. So then you times that, divide by that, so that's how you get that. So it's a small number. Okay, so that's why gravitational force is usually it's the smallest force in the universe compared to other type of forces. So that's gravitational force. And this one here, we also give a special name, we call that weight. So weight, it's a type of force, right? It's a type of force due to the planet, right? So it depends on what planet you are, right? So that's gravitational force. And gravitational force, right? And now let's talk about centripetal acceleration. So called AC, right? So AC, we derive that. That's equal to V squared divided by R. Okay? So if you have a UCM motion, This is the center. You have an object, right? So there must be a linear velocity going this way. And if you are here, this object must be having a linear velocity going that way. And the centripetal force must be going toward the center. And that's a net force. So it's the force, right? It's after you adding all the effect, after you adding all the forces on the object. So that's a net force. Okay. And FC and then AC must also be going, it can be larger, can be smaller. So AC also same direction. FC, AC, always same direction, right? Same direction, right? So you have velocity FC, okay? So if we are here, the AC is going this way and FC is going that way, okay? And notice that FC, right? It's perpendicular to velocity always. See that? Always 90 degrees. Let me change in color here. 90 degree, right? Always 90 degrees. So they're always 90 degrees. And that's why it can change direction. That's why centripetal force can change direction because it's 90 degree, okay? This is 90 degree, make it, right? So let's say if you have some kind of motion V going on right there. If you always apply a force on this object, which is 90 degree to it, the only thing you can change is the direction. You're not going to be able to change in the magnitude, right? So a perpendicular force, right? So perpendicular to the motion, right? To the motion. The motion is the V, right? Can only change direction. All right? So that's important, right? So if you have a parallel force, right? Say you have this, and your FC is going this way, and your velocity is going this way. So then this kind of, and this is not FC, Fn, right? Net force. If the net force is parallel to the V, then it can only, this net force can only change magnitude. Can only change magnitude of the velocity, okay? But this can only change direction of the velocity, right? So sometimes later, your velocity can be this way, but your FC will be this way, still 90 degrees, but this magnitude doesn't change. This V and this V has same magnitude, but different direction. The force is also changing direction, right? All right, I'm gonna clear that. So let's talk about UCM a little bit. So this is uniform. So uniform speed. And this is circular shape, circular trajectory, right? And this is just motion. So for UCM, it's a very complicated motion, actually. It looks simple, but you can see the force acting on it, net force, it's always changing direction. You see that? So net force, right, in UCM, always changing direction, constantly, right? Right, change direction constantly. So it's not like this, right? If you have a mass and you have a net force and there is no friction, then this is not changing direction. You see that? Always. So the A is always going this way. Okay? A in it's parallel. A and Fn always in direction. But this Fc is always changing. Okay? And not just that, your velocity is always changing too. Velocity direction always changing. So it's very complicated, right? So the velocity, right, which is called linear velocity, right? Also called tangent velocity, because it's tangent to the trajectory, tangent velocity, right? Or velocity in the tangent direction, tangential direction. So this V, it's changing direction constantly, change direction constantly. All right, so it's very complicated. All right, I'm going to stop there, okay? Until next time. Okay, bye-bye.